Hello and welcome again to another series of lectures in functional analysis. In the first lecture, we will discuss the dual spaces of the Lebesgue space, LP, the space of continuous functions, as well as the space of continuous functions with compact support. More precisely, we would like to describe the dual of LP, okay, in detail, up to an isometric isomorphism. And in the case of the continuous functions and continuous functions with compact support, we state the corresponding theorems and refer to the text in the literature for the proofs. So let us recall that if X is a norm vector space, then its dual is defined by or given by the set of all linear operators from X into R, and we denote a prime to signify the dual. So to characterize or the characterization of the dual spaces for LP is given by the following Riesz-Fischer theorem. So for this, let us suppose that I have a triple X sigma mu, and this is a sigma finite measure space. And let's say a P in 1 to infinity, okay? And Q is the dual of P. More precisely, the sum of the reciprocals of P and Q is equal to 1. Then the dual of LP is isometrically isomorphic to LQ. So more precisely, the map or the linear map J, so this is a mapping from LQ to the dual of LP given as follows. So G, I'll take an element G in LQ. So this should give me a bounded linear operator. Okay, so this is a bounded. This must be a bounded linear operator in F, or I should say in LP. So F here is in LP, and the action of this G evaluated at F is the integral of the product. From the previous lecture, we know that this indeed provides a bounded linear operator on LP. Okay. So this map is well defined, and in fact, it is an isometric isomorphism. So here, this integral on the right mimics the L2 norm, okay, or L2 inner product, but instead of L2 functions, we have an LP and an LQ function. Of course, you can see that this integral is well defined in virtue of the Holder's inequality. So alternatively, if you denote by a prime the dual, if we set Q to be P prime, so that P prime is the dual of P, then you can write the previous theorem as follows. So the dual of LP is isometrically isomorphic to LP prime. Okay. So the special case when P is equal to 2, L2 will be a Hilbert space. Therefore, this will be what? And we get the Riesz representation theorem because we know that for Hilbert spaces, the dual is isometrically isomorphic to the Hilbert space itself. Okay, and in that case, when P is equal to 2, we can apply the Riesz representation theorem. Okay, so you can think of this as the extension of the Riesz representation theorem in the case of L2. Okay, so however, instead of using P prime, we use Q as our exponent. To prove that a J is an isometric isomorphism, we need two, okay, theorems. The first one would be your Riesz theorem, or the Riesz representation theorem in LP. So here we consider a complete measure space. So without the sigma finiteness. Okay, so here let us emphasize that the measure space is also complete. Okay, so going back here, oops. We copy the assumption. So P is between 1 to infinity, and Q is dual. Then taking the LQ norm of G. So here we do not emphasize the sigma algebra and the measure for the norm. Okay. So this equation is valid for all G in LQ. This is the same as the supremum over all non-zero F in LP of the integral of the product F in G divided by the LP norm of F. Okay, so to establish this theorem, let us take an arbitrary element G in LQ, and let us suppose that G is non-zero almost everywhere. Otherwise, meaning if G is 0 almost everywhere, then G is the zero function in LQ. The product here will be 0. Therefore, the right-hand side will be also 0. So otherwise, both sides are equal to 0, and there's nothing to prove. Hence, it suffices to assume that G is not 0 almost everywhere. And to prove this equality here, we need to, or we show two inequalities. Okay. So for this, for F in LP, by applying the Holder's inequality, you end up with the following. So the integral of the product is less than or equal to the product of the norms. The product of the LP norm of G and F and the LQ norm of G. Then you get so you divide by the LP norm of X. Okay, so here let us say that F is non-zero, so that this is possible. So divide by F in LP and taking the soup over all such F. So by that we mean that the soup over all F in LP that is not zero so here we wish to divide the norm, okay, of LP. So dividing and taking the supremum produces this inequality. Okay, so that's one inequality. For the reverse one, we wish to establish a specific F, well, in terms of G, for which this supremum is attained. Well, that is accomplished by this function, F tilde, okay, so F tilde of X is, let's say, the absolute value of G of X raised to Q minus 2 times G of X, okay, provided that G of X is not 0. We need to impose this since, let's say, when Q is less than 2, this exponent here is negative, and therefore this will be in the denominator. So we need to be careful with that. Okay, not to divide by 0. In the case where G of X is 0, then we simply define F tilde to be 0. Of course, one can easily show that F tilde is measurable due to the measurability of G. Well, take note that the product of Q minus 1 times P, the product of Q minus 1 and P is equal to Q. And you can see this, that this is equivalent to, okay, dividing by P, and then dividing by Q both sides, you end up with 1 minus 1 over Q equal to 1 over P. So you divide by PQ both sides, and you have this equation, which is valid because P and Q are dual to each other. So computing the integral, okay, of F tilde raised to P, according to the definition of F tilde, this is the same as absolute value G raised to Q minus 2 times the absolute value of G raised to the quantity P. So here we ignore the set where G is equal to 0 because it will not, let's say, contribute to the integral. And simplifying this, we will have so q minus 2 plus 1, okay, times p, okay. But q minus 1 is times p is raised to q. So this is the integral of the absolute value of g raised to p. And this implies that, so you can now see that but first take note that this is greater than 0, okay, since g is not 0 almost everywhere. Okay, so thus f tilde is non-zero, and it is an LP, and its LP norm is equal to the LQ norm. This should be Q. LQ norm of X. We have a power P, and then we have a power Q. Okay. And dividing by or raising to the power 1 over P, you end up with the following. This must be, you can write this as Q over P. Okay. So with this, we can now what? So before we proceed, let us compute this, where f is replaced by f tilde. So this is what? F tilde, again, it is enough to consider the region where g is non-zero. Okay. So this is f tilde, you multiply by g. So you gain a power 2, and you end up with the integral of the absolute value of g raised to, again, this should be q. This must be q, okay? It's to the power q d mu. So this is the LQ norm of g raised to q. Okay, so with these two identities, we now have the following. So let's start with the right-hand side of the desired equation. Take note that, okay, this is the supremum, and since f tilde is just a specific non-zero element in LP, so the supremum must be greater or equal to this quotient. And we already know the numerator, so the numerator is the LQ norm of g raised to q. On the other hand, the denominator is the LQ norm of g raised to the power q over p. Good. Now we have the same base. Okay, so loss of exponents implies that this is the same as the LQ norm of x q minus q over p. Okay, there's a common factor q, so we can write that as q times the quantity 1 minus 1 over p. But since 1 minus 1 over p is equal to 1 over q, you end up with this. And this is the other, or the reverse inequality. So going back to the statement of the Riesz theorem, okay, so this will, as we shall see later, this will imply that the map J defined here is an isometry. Okay, hence J would be injective. To prove a surjectivity, we need to borrow a theorem in real analysis, namely the Radon-Nikodym theorem. So those who are not familiar with the theorem, let us state here for convenience. Let's start with 2 sigma finite measure spaces on the same set and on the same sigma algebra. And let us assume that nu is absolutely continuous with respect to mu. So what do we mean by a measure that is absolutely continuous with respect to another measure? So that is, if A is measurable, meaning it's in sigma, and the measure of A is 0 with respect to mu, then the measure of A on under nu is also 0. So null sets with respect to mu are also null sets with respect to nu. And to simplify this, we shall write, we should use the following notation. So roughly, we can say that nu is less than mu. And this notation means that nu is absolutely continuous with respect to mu. With this, we can find a measurable function such that our measure nu is the integral over A of this H with respect to the measure mu. Recall that integration over a subset is just the integral of the function times the characteristic function. And this is true for all A in sigma. And in addition, if let's say A or mu is finite, nu is finite, then we can choose this measurable function to be an L1. And in fact, this function can be shown to be unique. So we will not prove this theorem. So those who are interested, you may look at the book of Rodin, or there's also a proof provided in alt. Even in the case of the situation where nu is a complex measure. Okay. So that's a measure taking values in the set of complex numbers. Okay, so with these 2 theorems, the Riesz theorem and the Radon-Nikodym theorem, we are now in position to prove the Riesz-Fisher theorem that characterizes the dual of LP. So for each G and LQ, by the Rees theorem, okay, so we know that the supremum of this integral divided by the LP norm of f, okay, provided that f is not 0, okay, it's just the LQ norm of G. Okay, so you can put an absolute value here, or you can ignore it by simply replacing f by its negative. And in that way, you can see that this is the dual norm of JG. Recall that by definition, the numerator, so this numerator is equal to JG of F. So the first equation, meaning this one, is actually the definition of the dual norm, but with the absolute value. However, as I said, you can replace f by negative f, and you can ignore the absolute value in the definition of the dual norm. So this implies that J is an isometric isomorph. It's an isometry. Okay. And so J is injective. So isometry, hence injectivity, follows from the Rees theorem. So it remains to establish that J is surjective. And for this, we split the proof in two parts. So it remains to show that J is surjective. And by definition, this means that for any f in the dual of LP, there must be a G in LQ such that J of G is equal to F. And the latter statement is equivalent to J G of F is equal to F of F for all F in LP. So two functions are equal if you know if the function values coincide at all points in their common domain. So as I said, we will divide the proof into two steps. First, let us consider the special case where mu is finite. So the idea here, since our measure space is sigma finite, you can partition X into sets having finite measure, and then we apply on each set the finite case by a restriction, of course. So let's start with this case. take a measurable set A, that is A in sigma, then the characteristic function is in LP, and in fact the LP norm, and you can easily see this, is just the measure of A raised to 1 over P. And we know that this is finite since the measure of A is less than or equal to the measure of X. Hence, this quantity is finite. Now, take an arbitrary capital F in the dual of LP and define a function nu on the sigma algebra to R as follows. So nu of A is f of the characteristic function for all A in sigma. Take note that this is meaningful. I mean, the right-hand side is meaningful since this is an LP. Okay. Then nu is a assigned measure. So the difference between a assigned measure and a measure is basically just the values. So for a measure, you should have a non-negative value. For a assigned measure, you can allow negative values. Okay, so let us verify this statement. So the value of the empty set, okay, by definition, this is f of the characteristic function of the empty set, but that is identically 0. And by linearity of f, this is 0. Okay. Next, we show that nu is a sigma additive. So consider a countable sequence of measurable sets, and suppose that this is pairwise disjoint. Okay, now note that, okay, this characteristic function or the sum of these characteristic functions will tend to this one. But this is the same as the characteristic function of the union. And this is true pointwise in X. You could, of course, easily show this one. And moreover, note that we have this immediately. Okay, so pointwise in X. So you have that. Okay, and the other one, if you take, let's say, the magnitude of this, the absolute value, raise this to the power p. raise this to the power p. This is less or equal to. Okay, since the sets are pairwise disjoint, also this finite sum is either 0 or 1. Okay, and this characteristic function is also either 0 or 1. So this is less than 2 over p. And this constant function belongs to LP. Okay, since you have a finite measure. So we can now apply the so let us say that if we treat this as your constant function, this will be now in in L1. Okay. So by the Lebesgue dominated convergence theorem, you can see that this to the power p, okay, tends to 0 in L1. More, and this implies that we have this convergence in LP. By the definition of the LP norm. Okay, knowing this, and by the linearity and continuity of F, capital F, okay. So starting with the definition of nu, this is by definition f of the characteristic function of the countable union, okay. This is the same as f of this limit, okay. Of course, the limit is taken in LP. So here limit LP. Since f is continuous, therefore it is convergence preserving. So here, you now have the limit as n goes to infinity of f of this sum. Of course, now the limit here is taken in R. Linearity of f implies that f of the linear combination or f of the sum is just the sum of the f values. So this is now the series. By the definition of nu, this is nu of a sub I. So therefore, this implies that nu is sigma additive. So a sigma additive function on a sigma algebra having the property that the value of the empty set is 0 is what we call a signed measure. Okay, so there's a version of the Radon-Nikodym theorem for signed measures, and in fact for complex measures. But the one that we have stated a while ago is only in the case of measures. So what we do here is we produce a measure out from the signed measure nu. And this is the total variation. So consider the total variation denoted by this one, the absolute value of mu. So this total variation is a function on sigma to the set of non-negative numbers. And what we do is for a measurable set A, we define the total variation of mu at A as follows. So you partition A into a finite union of measurable sets. So here AI I from 1 to n is a subset of sigma, and this is pairwise disjoint. So among with this partition, we now take the sum of the absolute values of the signed measure nu at a sub I. And among all these sums, we take the supreme. So this is the definition of your total variation measure with respect to the signed measure nu. And with this, it can be shown that this is a sigma finite. Since nu is a sigma finite signed measure, okay, the sigma finiteness of nu follows from the finiteness of mu. Okay. In fact, it is a finite. This is a finite signed measure. We can show that the total variation is a sigma finite measure. A sigma finite measure. Okay. So we wish to show that this total variation is absolutely continuous with respect to mu. Okay, so to start, in virtue of the definition of the total variation measure, we consider an element in sigma and partition of A. So let's start with the sum. But before that, let us define sigma sub I to be the sign of the signed measure, okay, at A sub I. So the idea here is to replace the absolute value as follows. So we can write the sum of the absolute values as the sum of the sign times the real number nu of a sub I. Okay. The point here is that we can utilize the linearity of f. So this is now sigma sub I with the definition of mu. So this is f times the characteristic function of a sub I. So linearity of f leads to the following. So this is f of this linear combination, or I should say this simple function. Okay. Now, since this is pairwise disjoint, so this sum will be non-zero for precisely one index. Okay, so in other words, if this sum is 1, then this quantity must be either 1 or positive 1 or negative 1 on precisely one index. And the value of the characteristic function the value of a characteristic function is either 0 or 1. So the power of these two raised to p is also either 0 or 1. This implies that the integral d mu of this function is the same as the integral of the sum, but now without the sigmas. Because here, take note that we have the absolute value. Okay. And we know that this is what the integral of the characteristic function of a, and this is nothing but the measure of a. So raising to the power 1 over p we obtain that the LP norm of this simple function is equal to the measure of a raised to 1 over p. So therefore, looking back at this equation here, the first and the last term, applying the definition of the dual norm, this is less or equal to the dual norm of LP, of F in LP, times the LP norm of the argument. But we know that the second term on the right-hand side is just the measure of a raised to 1 over p. So now we take the soup over all such partitions of A. Okay, so this such partitions refers to this finite collection of pairwise disjoint sets in sigma whose union is A. So the supremum of the right-hand side would be the total variation. And you have the following. And this is true for any. A in sigma. So if A is in sigma and the measure of A0, then you can immediately see that the total variation measure of A0. And this is nothing but, or this implies that the total variation is absolutely continuous with respect to the measure mu. And this is the claim. Okay, now also we have mu to be less or equal to, according to the definition of the total variation measure, you have this. Okay, so applying the additivity of mu, you can show this easily. Now define, or let, I should say, let mu tilde to be the total variation minus mu, and according to the previous inequality, this is non-negative. Then this is a a sigma finite. In fact, it is a finite measure, and this is okay absolutely continuous with respect to mu. So indeed, to establish this absolute continuity, if A is in sigma and U of A is 0, then this is 0 by our previous claim. And therefore, okay, this is this is now equal to negative mu of A. Okay, we know that this is what we know that this is negative f of the characteristic function of A. Since A has measure 0, so this characteristic function is what equivalent to the 0 function. So therefore, this is 0. Since this is 0 in LP. So the next step is to apply this, or namely apply the Radon-Nikodym theorem for these two sigma finite measures, mu tilde and the total variation measure. Okay. Take note that you have this, and according to the previous claim, we have this. So therefore, we can apply the Radon-Nikodym theorem. So invoking that theorem, there exists L1 functions, let's say h and h tilde. This is the case because nu is finite. Okay, so let us emphasize here that nu tilde and the total variation is finite. And this follows from the fact that our measure space is finite. Such that h is the Radon-Nikodym derivative of the total variation measure, and h tilde is the Radon-Nikodym derivative of the measure nu tilde. So let us take the function g to be the difference. And so far we know that this is in L1, since L1 is a vector space. And for each A in sigma, you have the following. So this is equal to, okay, by definition of nu. And we can write this as follows. Okay. Simply by adding and subtracting the total variation measure. Okay, and this is by the definition of nu tilde. The Radon-Nikodym theorem implies that this is the same as the integral of h times, so that's the derivative, okay, the Radon-Nikodym derivative of the characteristic function of A d mu h tilde. And by the definition of G, this is the characteristic function of A times G. So this is only so far true for characteristic functions of measurable sets. Now, we would like to note that by linearity, this implies that f of, let's say, f is the same as this for all f in the span of the characteristic functions. Okay, so you just apply the linearity of f and the linearity of the integral. Since this is span, okay, is dense in LP, or I should say L infinity. And here you need to use the fact that the measure space is finite. And since that is the case, this is also a subset of LP. So the interested audience can look at the proof in the book about for this density. Since we have this density, okay, by continuity of f in LP, since L infinity is also a subset of LP, then we can extend the above equation also to all f in L infinity. Okay, so we can do this so far for L infinity functions because we only know at this point that G is L1. So in order for the right-hand side to be well-defined, for G in L1, you need that F to be L infinity by Holder's inequality. Okay. And with this, we aim to show that with this, we claim that G is in LQ. And this equation holds for all F, not only in L infinity, but also in LP. So there are two things that we need to establish here. So to show that G is in LQ, let us define the following set. A sub n. So let us define A sub n to be the set where G is positive and bounded by n. Then you can see that if we cut off G, okay, meaning we multiply by this characteristic function, so you ignore the values greater than n. And therefore, this is in L infinity. This is again a subset of LP. Now, adapting the proof of the Riesz theorem, let us define, let's say, F to be this absolute value of G raised to the value a while ago is Q minus 2, okay? That's G. And we know, so going back, if you go back to the proof, this is in LP. So let us separate that one. Then F is in LP. What else? If I compute the LQ norm of this function raised to Q, okay? So by the definition of the LQ norm, you have this, and this is the same as you can prove as before. That this is the integral of F times G d mu. By the way, since we have a cut of the function, so this F must be in L infinity, which is a subset of LP, of course. And here I need to correct this into LQ. And we know this a while ago using the same proof as before, that this is the same as the mhm. So this is the same as J, I should say F of F. And why is this the case? By applying this. Okay, as long as F is in L infinity. So here F is in L infinity, so that is reasonable. And likewise, the LP norm of F. So you follow the proof before. This is the same as the LQ norm raised to Q over P. So the proof of this are similar to the Riesz theorem. Okay. Using this, we can now conclude that applying the dual norm or property of the dual norm. So this is LP prime times F LP. Okay, and this is less or equal to okay. So let us write the first term as is, and the second term is this one. So you divide this both sides, and you end up with the following. The x prime. Okay. And from here, we now observe that since A n is increasing, we have the following. This functions raised to P is also increasing. In X, and we have, in fact, also the convergence this convergence pointwise in X. Okay, so take note that AN tends to AN tends to the or increases with the set where G is non-zero. Okay, so for non-zero values, you have a convergence. For G equal to 0, both sides are 0. Okay. By the monotone convergence theorem, okay, we can interchange the limits and by the way, this what this one. So I need to replace P by Q. So this should be LQ. and this must be also Q. So everything is fixed. The monotone convergence theorem implies that this is equal to this one. Okay, so by the monotone convergence theorem, we have this. Thus, after raising to the power 1 over q, and taking the limit here. Okay, so you get the finiteness of this. Okay, so but we know that this is finite since f is in dual of LP. So that f, or I should say g, is in LQ. Okay. And take note that we also need to show this one. Okay. Now we repeat the process. Okay. Applying the density. Okay. Of the span of characteristic functions now in LP. We also obtain. Okay, so you repeat the process. You can now apply f, or we can now use f to be in LP, since we know now that G is in LQ. And the right hand side again is meaningful due to the fact that or due to Holder's inequality. This is true for all f in. And from this, we now conclude that f is equal to j of g in LP prime by the definition of the map J. So that's the sigma finite case. So here we now treat the general case. So suppose that mu is a sigma finite. And from this assumption, there exists, let's say, a sequence of pairwise disjoint sets such that X is the union. In other words, X can be partitioned into countable sets, countable union of sets, wherein each of them has finite measure. Okay, so let us consider the restriction measure mu xi as follows. So So you just take the measure of A intersection x sub I. By monotonicity and the fact that the measure of x sub I is finite, then this is finite. Okay, so let us now take an element F in the dual of LP and set the set Fi. This is a map in the restriction measure space into R as follows. So F sub I of F is equal to F of F times x sub I. So for all F in LP let us retain the same space. Okay. So we retain the same space only at the measure. So from this, you can easily show that this is indeed in the dual space using the fact that F is also in the dual of LP. So from step 1, there exists G sub I for each I in LPX U x sub I such that F sub I of F is equal to the integral of F G sub I d mu x sub I for all F in LP. Okay, so from this, we now define, so we base these functions, okay? So I should really use x sub I. Okay, so there must be an x sub I here. So now we can define G by pasting these functions. So if x is in x sub I, okay, this is well defined. Since this is a partition of x. So there's a unique I that belongs to capital X sub I. So now we will show that G is in fact LP in X, and we can remove the index I here. Okay. So to apply the monotone convergence theorem, let us consider Y sub n, okay, to be the union of the first n sets. So for F in LP, Y n sigma mu, okay, the integral over yn of f g d mu, and you can partition this into integrals over x sub I f g d mu, and then you can use here the restriction measure. One can show this first for step functions, and then therefore for f times g functions, okay, by the construction of the Lebesgue integral. Since g is equal to g sub I on x sub I, we can put a subscript here. And this is what? The sum from 1 to n, f sub I times g. So let us label that according to here. Okay. So using that, you have this formula. Okay, and applying here the linearity, or the definition of f sub I should say. So you can look that this is the same as f times this must be small f. So f times the characteristic function of x sub I. You apply linearity of f and the definition of y sub n. You get this map here. Okay. So now we pass n to infinity. Okay. Since g, I should say this one again is increasing. Okay. First, we have. But before that, let us focus on the product. Okay, so since f, okay, this one tends to f. So you apply the same argument as before. We have this convergence in LP by the Lebesgue dominated convergence theorem. Okay. Also, by the monotone convergence theorem, you can show that again. G is in LQ, and the LQ norm of x, well, you can show that this is the limit as n goes to infinity of the characteristic function of yn times g in LQ. Okay, and this is the same as the limit as n goes to infinity of the LQ norm in yn. But we have, and this is also less than or equal to the LP norm of x, the dual norm. Okay, so you apply the same argument as before, and you end up with this inequality by applying the monotone convergence theorem. And therefore, we can now apply the continuity of capital F. So this is f of f times the characteristic function of yn. Okay, according to this limit here. And this is the same as the limit of the integral over x of f times the characteristic function of yn g d mu. Okay, since you have this the convergence of this in LP and G is in LQ, you can apply Holder's inequality to show that this is now we don't have the limit. Okay, show that this is f G d mu, which is by definition of the linear map J of G of F. And therefore, F is the same as J of G. This proves the surjectivity of J in the sigma finite case. So again, the main idea is to partition your X into sets, measurable sets having finite measure. You consider the restriction measure spaces and apply the finite case. And you combine the smaller sets. Here we denote that by yn, okay? The first n sets, and deduce or apply the monotone convergence theorem for Lebesgue integrals. So this completes the surjectivity of the map J, and hence the proof of the Riesz-Fisher theorem. So in the next lecture, we will discuss the other function spaces.